Let's finish this problem, and the last thing that we have to do is compute the antiderivative of the function and then its radius of convergence. Now note that we have to take the integral of the original power series, x to the n over 3 to the n, and then dx. Now how do we do that? Well, it's the same argument as in the case of differentiation. The series is nothing but it's a sum of infinitely many terms. So how do we integrate a sum of two functions? We integrate each of the functions separately and then add them together. So same thing here. We just have to integrate each term in this series. So it's called term by term integration, and then add all of those together, which in turn means that we actually have to flip these two symbols. So we will have sum 0 to infinity and then integrate this nth term, x to the n over 3 to the n dx. And what should we have here? Now be very careful right here. This is an integral with respect to x because it has dx. So this 1 over 3 to the n is a constant. So pull it outside. And what is the integral of x to the n? Use power rule. That's x to the n plus 1 over n plus 1. So you will have. And then we will also have a plus c as a constant of integration, but that will not affect the radius of convergence. All we need to do is just consider the power series and find this radius. Okay. Note that the center for this series is also 0, like the previous ones. Okay. Now we compute the radius of convergence of this new power series, and we'll do the same thing again. We'll apply ratio test. Okay, so what is our an? It is x to the power n plus 1 over n plus 1, 3 to the n. And therefore, the next term, the n plus 1th term will be, just plug in n plus 1 for n. So x to the power c n plus 1 plus 1, so n plus 2. Denominator, again, n plus 1 plus 1, so n plus 2, and 3 to the power n plus 1. So let's compute the limit as n approaches to infinity. Absolute value, okay, the n plus 1th term, write it down as it is. And then multiply, and nth term an you just flip. So you get n plus 1, 3 to the n divided by x to the n plus 1. We do the same thing again. Let's try to find the like terms and we'll cancel. See, the x terms will cancel and the 3's. And then we'll have the n plus 1 and n plus 2 that will not cancel. So let's see. The x, there is an extra x in the numerator, and you know that we have to keep the absolute value. And then an extra 3 in the denominator. So as before, we have that same term, absolute x over 3. And then we have n plus 1 over n plus 2. As you can see that this will always be positive, so we don't need absolute value. Okay, we do the same thing again. Pull out the constant, which is absolute x over 3. And inside the limit, in this expression with n, you just divide both numerator and denominator by n. Okay. So you will have absolute x over 3 limit. So same technique as before, divide both of these terms by n. So you get n over n, so which is 1 plus 1 over n. Denominator, same thing, n over n is 1 plus 2 over n. And we know that 1 over n will approach 0 as n goes to infinity. So the limit is the constant absolute x over 3 times 1, which is just absolute x over 3. So we got the exact same limit like the last 3 problems, right? And we know that less than 1 will imply convergence. And we know how to solve that inequality. The solution is exactly the same, and you probably have already guessed what our answer will be, right? Because the center is 0, interval is -3 to 3, therefore radius is again 3. So as you see that the radius of convergence of the original function and its derivatives and antiderivative, those new power series, all of them have the exact same radius of convergence. And don't think it's a coincidence, because guess what? This is true for all the functions. So if you take a power series, the radius of convergence of the original power series and the derivative will be same, and will be same to the power series that you get from the antiderivative as well. And this is a theorem, and looking at this particular problem, you can actually guess why they have the exact same radii. Okay, so this concludes the problem. Thank you.